When we talk about clean energy, we almost always look up, to the sun, to the wind. But what if one of the most powerful, most reliable sources of clean energy has been right under our feet this whole time? We're talking about the incredible, ever-present heat deep inside our own planet. I mean, just think about that for a second. The idea that the very ground we walk on holds the key to a constant, 24/7 power source. One that doesn't care if it's cloudy or if the wind stops blowing. That's the powerful idea behind geothermal energy. And at its heart, the concept is so simple it's beautiful. Geo for Earth, thermos for hot. It's basically the leftover heat from when our planet was formed, plus a little extra from the natural decay of elements in the Earth's crust. But, knowing that heat is down there is one thing. How do we actually get it and turn it into electricity?
Yeah, that's the real trick, isn't it? It's the multi-million-dollar engineering challenge. So let's get into it. How do we take that raw thermal energy from deep underground and turn it into something that can power our homes and cities?
Well, it really boils down to three main methods. First, you've got dry steam. This is the granddaddy of them all, the original method. You find a spot where steam is literally shooting out of the ground, you pipe it to a turbine, and boom, you've got power. Then there's flash steam, which is the most common type of plant running today. Here, you drill down and pull up super hot, high-pressure water. You bring it to the surface, the pressure drops, and it instantly flashes into steam. But the one to watch, the one that's really seen as the future, is the binary cycle. It's so clever because it can work in places with lower temperatures. It uses the Earth's hot water to boil a different liquid that has a much lower boiling point, and that liquid steam is what spins the turbine. Okay, let's actually trace this out, looking at a binary cycle plant. See that yellow pipe? That's the hot geothermal water being pumped up from deep underground. Now, here's the key. Instead of using that water directly, it flows into a heat exchanger. And see this separate red and blue loop? That's the secondary fluid. The heat from the geothermal water transfers over, causing that fluid to instantly vaporize. That vapor, that steam, is what spins the turbine and generates electricity. And the best part? The original water, now a bit cooler, gets sent right back underground. It's an elegant, closed-loop system.
And speaking of Iceland, man, if you want to see what's possible when a country goes all in on geothermal, there is no better place on the planet. This is a nation literally built from fire and ice, and they have figured out how to harness that fire to completely transform their society.
Just look at that number. It's almost unbelievable. In Iceland's capital, Reykjavik, pretty much every single home, 99.9%, is heated with geothermal energy. This isn't some far-off goal. It's been their reality for decades. But how they got there? That's the real story. You have to picture Reykjavik in the early 1900s. It was a city choked by the smoke from burning coal. Then, in 1930, they started a tiny project. They piped hot water from the ground to a school, a hospital, and about 70 homes. And from that small start, they just kept building, creating the largest geothermal heating service in the world. They didn't just clean up their air. They achieved total energy independence for their heating needs. And the benefits are just woven into everyday life. The hot water flows through pipes under the floors for this really comfortable radiant heat. But here's the really brilliant part. After it's used for heating, the water is still warm, right? So they pipe that runoff water under the sidewalks and driveways to melt snow and ice all winter long. No shoveling, no salt, it's just smart. So Iceland is an incredible success story. But it's kind of the perfect storm, geologically speaking. It sits right on a tectonic hotspot. So what about the rest of us? What about the rest of the world? This brings us to the next frontier, technology that could unlock geothermal energy almost anywhere. First, let's just get a quick lay of the land. Surprisingly to some, the United States is actually the world leader in total geothermal capacity. After that, you see countries along the Pacific's Ring of Fire, like Indonesia and the Philippines. Now, the common thread here is that all these places have a lot of natural volcanic and tectonic activity, which makes getting to that heat a lot easier. And that's the key question, isn't it? How do you tap into all that heat in places that don't have a convenient volcano or natural hot springs nearby? The answer is, well, you make your own. And the technology that aims to do that is called Enhanced Geothermal Systems, or EGS.
The concept sounds like something out of science fiction, but it's pretty straightforward. First, you drill deep down, miles down, to where the rock is incredibly hot but dry. Then, and this is the crucial part, you inject fluid at very high pressure to create a network of tiny cracks in that rock. You're basically creating your own underground reservoir. Then, you pump cold water down one pipe, it circulates through all those hot cracks, and you bring the now superheated water up another pipe to generate electricity. And the potential here, it is absolutely massive. A US government analysis estimated that EGS could unlock 90 gigawatts of power in the states alone by 2050. To put that in perspective, that's enough clean electricity to power tens of millions of homes. But, and it's a big but, this powerful technology comes with some very serious risks. Because when you start fracturing solid rock miles beneath the surface, you are fundamentally changing the geology of the area. And sometimes you can wake up forces that you didn't even know were sleeping down there. This quote from a Stanford geophysicist talking about a project in South Korea just sends a chill down your spine. It gets right to the heart of the danger. What was supposed to be a step forward for clean energy became a massive cautionary tale. What happened in Pohang is a stark reminder of what can go wrong. The high-pressure injection essentially woke up a fault line no one knew was there. And what's really scary is that even after they stopped pumping fluid, the earthquakes continued, getting bigger and bigger until it culminated in a magnitude 5.5 event. This wasn't just some minor tremor. It caused real damage, injured dozens of people, and was the largest quake ever directly linked to one of these projects. So, okay, let's step back and look at the whole picture. On the one hand, geothermal offers this incredible prize: renewable, stable, baseload power. That's the holy grail of renewables, power that's on 24/7, no matter what. But, on the other hand, it has its own unique downsides. For EGS, it's the risk of earthquakes. For traditional plants, it's being tied to specific locations. And for all of them, the upfront cost is astronomical. Just exploring for a good site can cost tens of millions of dollars with absolutely no guarantee of success. So, where does that leave us? What is geothermal's real role in our energy future? It's clearly not a simple silver bullet, but its unique strengths make it something we just can't afford to ignore. I think this really nails it. Geothermal is the quiet giant of the renewable world. It doesn't get all the headlines that solar and wind do, but it offers something they just can't: constant, unwavering power, day or night. The trade-off is that waking this giant is hard, it's expensive, and as we've seen, it carries some very real risks that have to be managed with extreme care. And in the end, that's the question we're all left with. The power is there, immense, and for all practical purposes, endless. But unlocking it safely, especially in new frontiers with technologies like EGS, forces us to weigh the incredible reward against a very real risk. It's a high-stakes question as we figure out how to power our future.